So in part F, we are given another compound which is used in alkaline batteries. In part 1, we need to, based on these half reactions, write down the net ionic equation for the reaction that has the greatest thermodynamic favorability. So that will be the one with the largest difference in the EMF value. So those will be these two reactions. So we can do this very easily. We see that the larger one will be the reduction reaction. So the other reaction we will have to flip around and add to the equation. So we flip this equation and we add it to this equation. So we will see that the electrons will cancel out, and on the left side we'll have 2 MnO2 plus zinc forming Mn2O Mn2O3 and zinc oxide. Simply from this side, the waters cancel out as well, and the electrons cancel out as well. The EMF of the cell, or the E value, will simply be the reduction minus the oxidation reaction. So 0.15 minus 1.28. This will give us 1.43 volts. In part 3, we need to calculate the value of delta G. Delta G is simply minus N times F times E. The number of moles is that we see that we have 2 electrons per mole of the reaction. So this will be minus 2 times 96485. That's how many coulombs 1 mole of electron has. And then we will multiply this with 1.43 joules per coulomb. That's for the volts. However, we need this in kilojoules. So what we can still do is divide all of this by 1,000, just so that we convert it into kilojoules. This will give us minus 276 kilojoules per mole. And then in part 4, our student claims that the total mass of an alkaline battery decreases as the battery operates because the anode loses mass. Do we agree or disagree? And well, we disagree. And the reason why is because the whole battery is sealed, so there's no leaving, or there's nothing is leaving the reaction, so the mass cannot decrease. So we can say its battery is sealed. So mass cannot change.